Welcome back to our comprehensive Windows x86 malware analysis bootcamp. I'm Ankit. In our previous video L1V3, we delved into computer architecture fundamentals including storage systems, protection rings, firmware and networking basics, and even got hands-on with analyzing memory and system call transitions. If you haven't seen that, I highly recommend checking it out. Today in L1V4, we'll trace the evolution of executable formats from the very dawn of computing to the sophisticated PE format we primarily deal with in Windows malware analysis. To help us visualize this, we'll be using an interactive timeline that you can see on the screen right now. We will then explore the crucial software build pipeline, how source code is transformed into these executable files, and finally we'll put theory into practice with a hands-on lab. I would highly suggest you to go through the full PE timeline by yourself at blog.FAUT.L.com. Link is in the description. While we are skimming and covering the important overview aspects here, the full timeline covers a comprehensive and detailed understanding that is truly beneficial. We will walk through each era understanding the key concepts and how they built upon each other. Our journey begins at the very foundation, binary basics. As you can see in this section of our timeline, computers at their core understand only binary, ones and zeros. This is because electronic components reliably represent these two states. We often use hexadecimal, which is base 16, as a more compact way to represent the binary data. Each hex digit corresponds to 4 binary bits or a nibble. For example, the binary 10110110 becomes B6 in hex. It's also critical to understand data organization. Bit a single 0 or 1. Nibble 4 bits. Byte 8 bits, the fundamental addressable unit. Word 16 bits, 2 bytes. Standard with 16-bit CPUs like the Intel 8086. DWORD or double word 32 bits, 4 bytes. QWORD, quad word 64 bits, 8 bytes. And then there's Endianness. This refers to the byte order for multi-byte values. Little endian, the least significant byte is stored at the lowest memory address. Big endian, the most significant byte is stored first. Common in network protocols. Misinterpreting endianness or data sizes can lead to completely wrong conclusions when examining memory or file structures. Next up, CPU registers. These are small ultra-fast storage locations built directly into the CPU. Think of them as the CPU's scratch pad, essential for any computation. You can see how registers evolved. 16-bit, we had general purpose registers like AX, BX, CX, TX, which could be split into high AH and low AL bytes. Then pointer or index registers like SP, BP, SI, DI, the instruction pointer, IP, and the flags register. In 32-bit, these were extended, prefixed with E, EAX, EBX, ECX, EDX, ESP, EBP, SI, EDI, EIP, and E flags. The original 16-bit registers form the lower parts of these 32-bit ones. For example, AX is the lower 16 bits of EAX. In 64-bit, registers were extended again, prefixed with R. RAX, RBX, etc. and new general purpose registers R8 through R15 were added. Similarly, EAX is the lower 32 bits of RAX. We categorize registers by their common uses and understanding these is key for reverse engineering. General purpose registers, EAX, RAX, accumulator, often holds arithmetic results, function return values and is used in some I/O operations. EBX, RBX or base historically is a base pointer for memory addressing. ECX or RCX is a counter used for loop counts and string operations. It's also the first argument in the x64 fast call convention. EDX, RDX or data used for I/O port access and holding parts of multiplication or division results. It's the second argument in x64 fast call. Index and pointer registers. ESI, RSI or source index, often a source pointer for string and memory operations. It's the third argument in x64 fast call. EDI, RDI or destination index, often a destination pointer for string or memory operations. It's the fourth argument in x64 fast call. ESP, RSP, stack pointer, critically important, it always points to the current top of the stack, modified by push, pop, call and ret instructions. EBP, RBP, base pointer typically points to the base of the current function's stack frame, allowing access to local variables and arguments. EIP, RIP, instruction pointer. This register is central to execution. It holds the memory address of the next instruction the CPU will fetch and execute. E flags, R flags. This register doesn't hold a single value, but a collection of individual bits called flags that reflect the outcome of previous operations or control CPU behavior. Segment registers CS, DS, SS, ES, FS, GS. These are 16-bit registers, remnants from older segmented memory architectures. CS, code segment. points to the segment containing the current executing code. DS, data segment, default segment for data access. SS, stack segment, points to the stack segment. ES, extra segment, an additional data segment. FS and GS, in modern Windows, these are used for specific purposes. In 32-bit Windows, FS typically points to the thread environment block, TEB, while in 64-bit Windows, GS serves a similar role. 64-bit additional GPRs R8 to R15. These provide more general purpose registers for 64-bit code. R8 and R9 are used for the 5th and 6th arguments in the x64 fast call convention. Malware analysts constantly track register values when debugging. EIP RIP dictates control flow. ESP RSP manages the stack, and FSGS can reveal stealthy attempts to query process information. Now we arrive at machine code. This is what CPU actually understands: raw binary sequences or opcodes that trigger specific hardware operations. We usually represent machine code in hex. For example, 55 in hex is push EBP and 89E5 is move EBP ESP. This is the standard 32-bit function prologue. As noted on the timeline, sometimes the same assembly instruction can have different machine code encodings. x86, x64 instructions have variable lengths and can include prefixes, an opcode, a ModR/M byte, an SIB byte, a displacement, and an immediate value. And for 64-bit, we have the REX prefix, which extends capabilities to operate on 64-bit operands and access the additional registers. Recognizing common byte patterns for function prologues, returns, and calls is incredibly useful for malware analysts. Directly reading machine code is tough. That's where assembly language comes in. It provides human-readable mnemonics for machine code instructions. An assembler translates assembly into machine code, while a disassembler does the reverse. It's important to distinguish disassembly from decompilation, which is the process of turning machine code back into high-level code like C++. Let's also touch on function calling conventions. Like the 32-bit std call used by many Windows APIs, arguments are pushed onto the stack right to left. The function is called and the callee cleans up the stack. The return value is usually in EAX. Modern operating systems give each process its own virtual address space, which is mapped by the operating system to actual physical memory. This virtual space is typically organized into kernel space, operating system memory, inaccessible to user programs. Stack grows downwards, used for function calls and local variables. Heap grows upwards, used for dynamic memory allocation. .bss and .data for uninitialized and initialized global or static variables. .text for executable code. The image base is the preferred starting virtual address for a PE file. If that address is taken, the operating system performs rebasing. The base relocation table .relog section contains information to fix up any hard-coded addresses. The PE file loading process is intricate. The loader reads headers, maps sections into memory, processes imports by loading DLLs, performs relocations if needed, and finally transfers execution to the entry point. Now let's discuss file identification. A key part of this is magic numbers, special byte sequences at the beginning of a file that identify its type. For PE files, it's MZ4D5A at the beginning and then PE50450000 at an offset specified in the MZ header. These signatures allow quick identification. Files also have header structures containing metadata. The P format has a chain of headers. Before sophisticated formats, we had formats like the .com file. It was essentially raw x86 machine code loaded at a fixed offset at 0x100 within a 64 kilobyte memory segment. It had no header and was very limiting. The MZ revolution brought the .exe format to MS-DOS, identified by the MZ signature. For Mark Bukowski, it introduced a header and a relocation table, which allowed exes to be loaded anywhere in memory and break the 64 kilobyte barrier. This brings us to the portable executable format, the standard for all modern Windows versions. It's derived from the Unix COF specification. Key characteristics include portability, extensibility, dynamic linking, and a section-based layout that organizes the file into logical sections like .text, .data, and .rsrc or resource. The PE format distinguishes between P32 and P32+ or 64-bit, primarily in the optional header. Understanding PE structure is step 1 in static malware analysis. DOS MZ header starts with MZ. The most important field is E_LFA new at offset 0x3c, which points to the PE header. P signature and COF header. This contains key fields like the target machine type, number of sections, a time date stamp, and characteristics flags. Example, if it's an exe or DLL. Optional header contains critical loading info like the address of entry point, image base, subsystem, GUI or console, and security flags. Data directories. This is an array within the optional header that points to other crucial data structures like the import, export, and resource tables. P files organize their content into sections. The section table, an array of headers, describes each one. Key fields in each section header are its name, virtual size, virtual address, size of raw data, pointer to raw data, and characteristics. Memory permissions like read, write, or execute. Ploader maps the sections defined in the file into the process's virtual address space, which is typically treated as a single large segment, which is flat memory model by the running code. To understand this difference, kindly read the segments versus sections part of the interactive timeline. Now, common section names are .text, executable code, read, execute, .data, initialized global variables, .r data, read-only data, and strings. .i data, import tables, .rsrc, resource like icons, often abused by malware. .reloc, base relocation information. Unusual section names or permissions like writable code are huge red flags in malware analysis. Now for some advanced concepts, import and export tables. The import address table or IAT is filled by the loader with actual function addresses. Malware abuses this via IAT hooking or by resolving APIs dynamically to hide its intentions. About symbols and debug information. Symbols map memory addresses or offsets to human-readable names, function, variables. Debug information provides more detail for source-level debugging. P security features. Features like ASLR and DEP mitigate exploits. Malware constantly tries to bypass them. Modern languages like Go binaries are often large, statically linked, and don't rely on typical Windows API imports, making initial analysis different. Resources .rsrc, frequently used by malware to hide encrypted payloads. TLS callbacks, execute before the main entry point, a favorite malware trick for anti-debugging and early execution. Packing or encryption, a common malware technique where a small stub unpacks the real code at runtime. Signs include few imports and high entropy. And that completes our tour of P format evolution. Okay, it's break time now. You can pause the video, take a break if you need. See you soon. A fundamental process in software development that is absolutely critical for malware analysis is the software build pipeline. We often see complex executable files, but how does a developer's simple text file become one? That's what we will explore. If you look at the screen, you will see our interactive guide. The journey from code to execution isn't the same for all programming languages. There are three main models. First, we have the model that is most important for our work, statically compiled languages. This is the world of C, C++, and more recently Go and Rust, which are becoming huge favorites for malware authors. We are going to walk through this pipeline step by step. It all begins with the source code. This is the human-readable script written by the developer. As you can see in the notes, for malware, the choice of language here is significant. Go and Rust are popular because they make it easy to create a single large executable file with no dependencies, which is a nightmare to reverse engineer. The raw text from these files is then fed into the next stage, the preprocessor. This stage is most relevant for C and C++. The preprocessor doesn't understand code. It just follows simple text-based rules. It handles things like including header files with #include, expanding macros defined with #define, and even conditional compilation using #ifdef to include or exclude code. This is a powerful obfuscation tool for attackers. As you can see, the size macro is literally replaced with the number 10. This is a simple example, but you can imagine how complex macros could hide the true logic of malware. The clean expanded code from the preprocessor is then passed to the brains of the operation, the compiler. The compiler translates the human-readable code into low-level assembly language. This is a multi-step process involving lexical analysis to break code into tokens, syntax analysis to build a structure, and semantic analysis to check for logical errors like type correctness. Finally, it performs code generation. A key step here is optimization. This is a double-edged sword. It makes normal programs faster, but malware authors use it to scramble their code, making it much harder for us to analyze. Let's look under the hood at a code data structure the compiler builds. This is a simplified abstract syntax tree for a line of code. The compiler builds this tree during syntax analysis to understand the code's grammatical structure before generating assembly. The assembly code generated by the compiler is still text. To make it something the CPU can actually understand, it's sent to the assembler. The assembler's job is simple but crucial. It performs instruction encoding, converting text mnemonics into their binary machine code equivalents or opcodes. It also handles label resolution, converting symbolic labels for loops or functions into actual memory addresses. The output is one or more object files. Here you can see that the simple instruction move EAX1 becomes the hexadecimal sequence B801000000. This is what the CPU actually reads. Now we have our code in binary format, but the pieces aren't connected yet. That's the job of the linker. The linker is where everything comes together. It performs symbol resolution, matching function calls with their definitions across different files. Its most important job for us is relocation. Let's look under the hood. When one object file is compiled, it doesn't know the final memory address of a function in another file. So it uses a placeholder. The linker's job is to patch this placeholder with the final correct memory address, as you can see in the after state. Crucially, the linker is also where library integration happens. This is where a choice is made between dynamic linking, which relies on system DLLs, and static linking, a key technique for malware that bundles all necessary libraries into one file. After the linker has patched all the addresses and combined all the files, it performs P file creation, constructing all the headers and sections to produce our final product, the executable. This is the final P file that the operating system can run. Let's look at its basic structure. It's a structured file with headers and different sections for code and data. The P header highlighted in red is the most critical part for an analyst. It's the file's table of contents, and it's where our analysis always begins. For a deeper dive, you can check out the interactive timeline of executable linked here. Let's look at the other models so you can see how they differ. Languages like Java and C# are compiled first to an intermediate bytecode, not machine code. Then a virtual machine on the target computer compiles that bytecode into machine code just in time as it's needed. It's a hybrid approach. And finally, interpreted languages like Python, here there's no build step at all. The interpreter program reads the script line by line and executes it directly. The reason we focus so heavily on the compile model is because that's what most malware is written in. To wrap up, let's look at some key terms you'll encounter. Here you will find a more detailed breakdown. We have key build concepts like intermediate representation and link time optimization. We have the specific build tools, the compilers, linkers, and build systems that automate this whole process. We also have a list of common optimizations like inlining and dead code elimination that you will see in the while. And finally, the section on debug information, which explains why finding a PDB file path in a binary is a gold mine for an analyst. As you can see, the build pipeline is not just a simple conversion process. It's a series of complex stages, and every single stage provides opportunities for a malware author to optimize for evasion, obfuscate their code, and make our job as analysts more difficult. Understanding this process is the first step to defeating them. Please feel free to explore this interactive diagram further. Link is in the description. Okay, it's lab time now. You can pause the video, take a break if you need. See you soon. I hope you guys are back. Now before we start our lab, please read the safety note. Now for our hands-on lab, we are going to take a simple C program, compile it with different settings, and immediately examine the result of each change in binary ninja. I've already created batch scripts to make compilation easier. We are using GCC GNU compiler collection from MingW, but the principles are same for other compilers. Here's our starting point, a simple program saved as hello.c. First, we'll compile with full debug information and no optimizations. This is our baseline, best case scenario for analysis. We are about to answer the very first question. Where does this program really start, and how do I find the main logic? In the symbols list, we can find the start symbol, which is the entry point. You will see it points to a function named maincrt startup. This is the C runtime CRT startup code that prepares the environment before calling your main function. You might also spot winMainCRT startup in the symbols list. This is a common side effect of how the MingW linker works. It sometimes includes this startup code for GUI apps as a dependency even when building a console app. Remember, it's just unused code. MainCRT startup is the only one that actually runs. If you look at maincrt startup and follow the call instructions, you will see that it eventually calls your main function. This is how you can manually trace from the true entry point to the programmer written code. Because we use the gdebug flag, you don't have to trace it manually this time. Just look in the symbols tab, you will see main is clearly named. Looking at the main function, you will see a direct translation of our C code. The first printf is replaced by a call puts. The compiler does this by default for simple strings ending with a new line because puts is more efficient. A visible for loop structure, an explicit call square instruction inside the loop, a final call printf for the total string which is kept as printf because it uses a format specifier. By looking into try summary, we also notice extra sections in the binary like debug info, debug ranges, which hold all this debugging information. Searching for strings might also reveal the source file name. Now let's compile with default settings. The true entry point is still main CRT startup. And the machine code in the main function is identical to the debug version. Looking at the main function in the symbols tab, you will notice its name has changed from main to _main. This is a C language feature called name decoration. Many compilers on Windows, including MingW, automatically add an underscore prefix to function names. The CRT startup code is actually looking for _main. So why did it show as main before? The gdebug flag provided extra information that included the original source code name. Without it, Binary Ninja shows us the raw decorated symbol that's actually used by the linker. By looking into triage summary, we notice while those debug section headers might remain, the useful content inside them is gone. You can no longer find the source file name hello.c, which is a direct result of removing the G flag. Before we continue, it's important to know that GCC has several levels of optimization. The O flag controls this. Here are the most common ones. We'll compile with O2 optimization level now. This version will show a significant transformation due to the O2 optimization flag. The most dramatic change is that the entire for loop has been eliminated. The compiler performed an optimization called constant folding. It analyzed the loop, calculated that its final result would always be 285.11d in hex, and simply replaced the entire calculation with a single move instruction that places the hardcore result onto the stack. Because the loop was removed, the call square instruction is also gone. This is the result of function inlining combined with constant folding. The compiler effectively absorbed the square logic into its compile time calculation. Even though square is no longer called from main, if you search for it in the symbols tab, you'll likely still find its original code. It now exists as unreferenced code, which the linker kept even though it's no longer part of the main execution path. By looking into triage summary, we can notice that debug section headers are still present. It's important to remember that meaningful debug information is generated by the G flag, while code structure is changed by the O flags. The size and content of these sections should be virtually identical to the default build, as they are likely artifacts from the linked C runtime libraries. The O2 flag's real impact is on the text section, where it completely transformed the code. Now for the malware author's favorite combo, optimize for size and strip all non-essential symbols. Let's compile. This is what RE often looks like, optimized code with no symbols to help us. The first thing you will notice in the symbols tab is that it's practically empty. All the meaningful names like main, square and main CRT startup are gone. The S flag instructs the linker to discard the standard symbol table to reduce file size and significantly hinder analysis. Since there are no names to click on, we must now manually find the main code. Looking at the entry point by clicking start symbol in symbol table, we can follow the execution flow from there. This will lead to the anonymous CRT startup code. From here we can trace the call to find the main logic. While navigating to this anonymous main function, we can observe that its code is identical to the highly optimized O2 version. However, it was compiled with OS, which is optimized for size. For malware authors, minimizing file size is often more important than maximum speed, and OS enables optimizations that don't increase code size. While the result is the same here, on larger programs, OS might choose smaller instructions even if they are slightly slower. The main function contains the call puts and the hard-coded result 11d for the final printf. The challenge here is that you have to understand this optimized logic without any names or symbols to guide you. Let's look into triage summary. Unlike the previous builds where we saw debug section headers, the sstrip flag instructs the linker to remove all debug sections entirely. Its purpose is to create the smallest possible executable by removing all non-essential information, which includes both the standard symbol table and all sections related to debugging. An analyst's first step is often to check the import table to see what a program can do. Now we'll compare the standard way of linking a library with a more advanced method that malware uses to hide its capabilities. First, the standard approach. We'll use this simple code that calls message box A directly. Using this code now, let's hide that import. We'll use the same functionality but load the library and find the function's address manually at runtime. Let's compile both of them. After opening compile time executable, in the triage summary under imports, we can see a clear entry for message box A under user32.dll. An analyst immediately knows this program creates pop-up boxes. Now let's look into runtime executable. Checking the import table again, we observe that the user32.dll and message box A are gone. The program now imports load library A and get proc address A from kernel32.dll. If we open the runtime executable in die and check its strings, we can find user32.dll and message box A. These are now the primary clues to the program's true intent. We have stripped symbols and statically linked APIs. Let's get rid of the standard entry point now. We'll use this new file, customEntry.c, where we have renamed our main function to custom entry. Now we'll compile this using two special flags to tell the linker to use custom entry as the only starting point. Pay close attention to the eCustomEntry flag. Why the underscore? This is a crucial detail called name decoration or name mangling. By default, the GCC compiler on Windows adds a leading underscore to C function names to signify their calling convention. How arguments are passed. The actual symbol name inside the compiled file becomes underscore custom entry. We must provide this decorated name to the linker for it to find our entry point. Looking at the start symbol, it no longer points to main CRT startup. Instead, it takes us directly to the custom entry function, which will have a generic name because we also stripped it. The program's execution now begins immediately with our code. Looking through the symbols list, we can find that main CRT startup and the other C runtime set of functions are completely gone. We have bypassed the entire standard startup routine. And that brings us to the end of L1V4. As you saw, every single compiler flag changed what the final binary looked like inside Binary Ninja. In our next video, L1V5 will build on this and explore more advanced P concepts. Thank you for joining me. Stay curious, keep learning. Peace.